So thanks for coming, everyone. I'd like to talk today about some work I've done on directed type theory. And this is joint work that I'm currently working on with Marcello Fiore. And it's work in progress, so the things that I'm going to report on are not completely finished yet. The stuff I'll talk about mostly today is finished, but there's still more things to do. So I hope you'll forgive me if I don't answer all of the questions about everything to do with directed type theory today. This is a talk about directed type theory, and in fact, today I'm going to do something which is perhaps a bit sadistic, which is I'm actually just going to talk about type theory. I'm not going to say anything at all about semantics. So if you want to hear about categories or higher categories or directed homotopy theory, things like that, I'm actually not going to talk about those things. Yeah, so some of you may find that very refreshing. Some of you may find it sadistic. So it just depends on who you are, I guess. Yeah, so now, well, I guess I'm not quite telling the truth. I will say something about categories and infinity categories, but very little. And I'm not going to give a semantics for the theory that I'm presenting. So what's the idea? Well, let me start with some kind of well-known in these circles history. So the first thing is the kind of observation of Hofmann and Streicher. And I'm sure most of you are very familiar with this. I think this is 96 in an abstract, and then 98, which is that types in Martin-Löf type theory, which I will henceforth just write as MLTT, form some kind of higher dimensional groupoid. So they observed that, well, you can compose terms of identity types. This gives you something that looks like the composition operation in a category. You can construct inverses, so it starts to look like a groupoid. Now, the problem, of course, is that those things don't compose to give you a strictly associative composition or a strictly unital on both sides composition. And so you don't really get a groupoid until you mod out by some higher dimensional propositional equalities. But it's something like that, and this was made a bit more precise in subsequent work by Vandenberg and Garner. So this was made precise in the following theorem, which is due to Vandenberg and Garner. And then there's an independent proof also due to Lumsdaine. And I guess this was from 2007 or 8 or something like that. I don't know. Anyway, so it was quite recent compared to the Hofmann-Streicher result, which is that types in Martin-Löf type theory form weak infinity groupoids in the sense of Batanin and Leinster. And I guess that one has to be a bit careful here, because I believe that in the result of Benno and Richard, they show that it's the Batanin weak infinity groupoids, and I think Peter's result is just that you get Leinster weak infinity categories, but Peter's not here to refute that, so you can just take it as given that that's the case. I'm pretty sure that's the case. Anyway, this is kind of the general result, that you get these weak infinity groupoids out of types in type theory. And what's the kind of question that you ask when you start thinking about directed type theory? Well, the question is, so this is kind of the principal question that I'm aiming to try to answer, which is that, oh, there's Peter. You're too late to refute something I said about your work. So, so the question is, of course, is it possible to describe a type theory in which types form, and then again, I'm going to assume weak, of course, infinity categories. And of course, I mean weak infinity categories that are not necessarily groupoids, okay? And so the kind of sort of related question is, similarly, can we get, in this way, weak, well, let's just say infinity in categories. So for example, can we get infinity 1 categories as types in some type theory? And so this is a kind of question that people have worked on in the past. And so there are some results along these, in this direction at least. And I think it's worth kind of recalling those. So I think the first result along these lines that I know of is due to Steve Audi and Andre Bauer in a preprint, which I think is from 2001 maybe, but I don't think it ever appeared anywhere. So that's a result of Audi and Bauer. I think it's 2001 or so. And what they did was they studied a type theory with reductions. And the idea is that you have types, and you have terms, and then you have a notion of a reduction between terms, which is a kind of two-cell. And then they had a kind of internalization of those two cells as terms in some kind of identity type. And they proved that that these give you a 2 category, so get a 2 category in this case. So this is a kind of finite dimensional approximation of the kind of result, or the kind of theory that one would be after. The next result along these lines is Harper and so Bob Harper and Dan Licata. And that's from 2011. And it's quite similar. So similar to that. And they proved you have a model in cat, the 2-category cat of their theory, and they gave some applications. And there are various other people who I think have worked on things that are quite similar in various ways to the kinds of things that I'm going to talk about, so I'll mention some of them, not necessarily in chronological order, but let's say Claudio Ermita, John Power. There are probably other Australians that I'm leaving out who have thought about these kinds of things. Let's see, who else? Andre Joyal gave a talk the other day, and the things that he's thinking about are quite close along these lines. Eric Finster has worked on similar things. Noam Zeilberger has also thought about similar things. And I think a lot of the people working on, so researchers in rewriting, and those are most of the people that I have in mind are in France. So I'm not going to list all of the names of people working in this area because there are many of them, but I think that the people working on rewriting in France, so people like Philippe Gaucher and Yves Guiraud and all of these guys, they were thinking about very similar kinds of things to this sort of theory. François Métayer. Many of those people were working on similar things. And I'm sure there's probably someone in the audience who's working on this that I haven't mentioned, and so I apologize. Okay, so obviously people have tried to answer this question, but I think the concrete results that we have so far are only in low dimension. And so I want to give something today that actually does give a higher dimensional category. And so I want to, first though, before I get into the details, I want to give you a kind of list of some design criteria that I had in mind when thinking about this problem that I think are kind of important for anyone who wants to tackle this problem to think about. So design criteria. And each of the things that I'll mention may be harder or easier to satisfy in various cases, depending on what exactly you want to do. So I want to say it's not too ad hoc. Because obviously, I can write down a type theory that gives me a, say, a strict infinity category by just recreating the definition of a strict infinity category in type theoretic notation. That's not what I want. I want something more type theoretic in nature than that. So what's the next thing? Relatively easy to use. So this one I think is important because, and the relatively there is also important because my impression of working with directed type theory is that it's going to be harder to use in general than ordinary Martin-Löf type theory. But we don't want it to be too hard to use. So to give you a kind of example, when we started working on this, we actually had a theory which was a substructural type theory. And there, because you've gotten rid of the structural rules of type theory, it becomes very difficult to use. And in fact, I think it turned out to be too difficult to use, which is why the theory that I'm going to present is not substructural. And then you would like the kind of obvious things like that it's truly higher dimensional. And I think it ought to be somehow conceptually reasonable as well, which is a third thing. But these are the kind of design criteria that we had in mind when thinking about this theory. And so I hope that by the end of today, I'll have convinced you that the very simple theory that I'm going to present actually does satisfy these criteria to some extent. You may disagree a bit about either of these two, but hopefully, yes?
Because one design criteria you might have secretly had in mind, I wonder, is that we'll have a model in cat.
Yeah, of course. So, I mean, let me tell you all of the intended models. So I'm not going to say anything about the semantics. We have a sketch of a semantics in several simple cases, but it's still a bit ugly, so I'm not going to say anything about it because, but the sort of intended semantics ought to be, well, depending on which infinity in you want, but just in general, if you just want general infinity categories, then you ought to have models in cat, posets, let's say infinity cat for strict infinity categories. You might want quasi-categories. And you might want things like models in the directed homotopy theory of Grandi's and his collaborators. So those are some kind of cases where you would like to have models. And there are probably many other examples where you'd like to have a model, but those are some of the kind of test cases. And at this point, we have a kind of sketch of semantics in these two, and it seems to extend also to, oh, pardon me, not to that one, but to quasi-categories, but that needs to be verified. And Yes.
Do you think, so it sounds as though you're intending to work in this theory, it's not just the kind of object of study.
Yeah, so that's another thing that I will say something about a bit later, because, yeah, of course you want to be able to work in the theory. I mean, it would be, ideally, you would want to have a proof assistant that allowed you to manipulate proofs in the theory in the way that we can manipulate proofs in Coq using ordinary Martin-Liff type theory. Yeah.
There's something which I miss here, or maybe just me. So before, the equality type has a very natural meaning, right? It means
Yes.
equality.
Yes.
So what's the meaning?
I mean, the meaning, yeah. I need to, so I don't want to talk about semantics, but I mean, it's kind of clear that if you have a type that looks like a identity type but is directed, then the intended semantics ought to be the HOM.
No, what does it mean? I mean, equality is very clear, so logical.
Yeah, well, so if you look in quasi-categories, in quasi-categories,
Sure, but I want to know what it means. I mean, equality means something.
Equality only means something if you start with a thing which has a notion of equality, like a set or in any good way. Om only means something if you start with a thing which has a notion of Om, like a category.
take A to be a simplicial set, then you would want the sort of HOM type to be intuitively the map from A to the delta 1 down to A cross A. That's kind of the...
Let's delay this.
The arrow, the arrow category. You know.
My question cannot be communicated easily.
Okay.
First thing is approximation, or does that help you? Or?
Sure, that would help us, but what would it mean, approximation, right? I mean, okay, fine. That would make sense. Yeah. I mean, equality makes sense. I'm not talking about sort of mathematical models. I mean, intuitive meaning.
I'll tell you the intuitive meaning in a moment. Okay. Yeah. I want to say something about the actual theory. So now I'm going to tell you the actual rules. So the first thing is that I'm going to put some restrictions on the theory that I'm working with to make it simpler to handle. In particular, I don't want to throw in a bunch of arbitrary type formers and now say I'm going to work in there. I want just a very regimented set of type formers so that I can play with this test theory. Okay. So let me. So I have several criteria that I'm going to mention. So directed type theory, DTT, we will require 1. So the usual structural rules of Martin-Liff type theory. So for the purposes of today, I'm going to assume that we have a fixed base type, which I'll write as bold B. And I'm going to assume that I have directed types. Or what I'll call, I'll probably call them directed types, but you also might call them HOM types. And satisfying rules given below. So those are the 3 things that I'm going to assume at the moment. So I'm not going to throw in pi's, I'm not going to throw in sigmas, I'm not going to throw in arbitrary inductive types or anything like that. I just want a very regimented set of basic things that I need, and that's it. Okay? So now what are the rules for this directed type? Well, the first 2 rules should be very obvious because they're going to be exactly the same first 2 rules that you give when you give the Martin-Liff identity type. So that we have a formation rule, and the formation rule says that, and I'll write this in a sort of parameterized way, but because we have the ordinary structural rules, there's no reason not to. So if I've got a type A, and I'm going to adopt the usual convention that if I write this, I'm assuming there's some ambient context, but I don't want to write it, okay? So if I've got a type A, then I've got, for any x of type A and any y of type A variables, then in this open context, I get a new type, which I'll write as A with a underline xy. And it's kind of, you want to think of it as being like the HOM. Okay? So I think of x and y as being some objects in a category or so. And this is the HOM. That's the intuition. So this is the formation rule. So one point about notation is that in the future, when I have some list like this, I'm going to start becoming very sloppy and not writing the of type A everywhere. I'll just write x, y, both of type A. Okay, so don't, for those who are not familiar with this kind of sloppiness in type theory. Okay, so what else? We have an introduction rule. And the introduction rule, again, it's exactly what you already know. It's that if I've got a type A, then I've got, in particular, a identity, which I'll write as R of x. And that guy goes from x to x. And again, the intuition should be clear. R of x is the identity arrow or cell on the object or other cell x. Okay, so now what do I say about the elimination rule? Because I've given you formation and introduction. Elimination is the next natural thing, and this is where things have to be different. So before I give you the particular elimination rule I'm going to use, I want to recall a little bit just intuitively how we can think about the ordinary Martin-Liff elimination rule. So this is the ordinary id-type elimination rule from Martin-Liff type theory. It says that, sort of written in the same style, it says that if I've got x and y of type A, and I've got some path going from x to y, and I've got some type that varies over those paths, well, in order to know that I always get a term of this type, it suffices to test that I get a term of those reflexivities. So I've got an E of type E when I've substituted x for y and r of x for z. Then I get x, y, a, z of type id A, x, y, giving me this j term that everyone's probably familiar with. X, y, z of type E. And
Can I slow you
yes.
down there and ask you to reread this rule?
Yes.
You were hiding it as you were writing.
Pardon me. It's the usual elimination rule for identity types. So I've got a type, and it depends on an identity proof. And I want to know that I can construct a term of this type E. So how do I do it? Well, I test on the generators, which are the reflexivities. And I see that I've got a little e there, and that tells me that I've got actually a term for any path, for any identity proof. I've got a term of that e at that identity proof. Okay? So
You wrote ID.
yes, I'm talking. This is the ordinary Martin-Liff rule.
Okay.
I'm going to contrast that with the rule that I'm going to give. But in order to get there, I want to give you some intuition so that I can answer Torsten's earlier question. And to do that, I want to start with this, because this is something that is kind of the starting point for the idea in some sense. So what's this saying? Well, it's saying something, I mean, just to sort of be as intuitive as possible and not give you any real sort of serious description of what this means in a model or something. It's saying that, well, I've got this property E, and I've got this path, and I want to know whether or not the property holds, the big E holds. So, well, what do? I just contract that path down to a point, and then I test it. Okay? And the reason that we can do this from a kind of perspective of thinking of type theory in terms of homotopy theory is that E itself is a homotopy theoretic property. And if I want to know whether or not a homotopy theoretic property holds over some base type, and I've got a path in the base, well, I can just contract that path down to a single point. And if it holds then it's going to hold in general if I expand the path back out. Now, we can't expect something like that to hold in the directed case, because this is clearly not a valid principle for reasoning about categories. But what we can do is something a little similar, which is to look instead, maybe I can erase that. Look instead at, well, think a bit about how you should reason about categories. So for categories, that isn't going to work. But what you might think is something like this. And I'll draw the picture, and then I'll tell you the rule. So here I've got not just a single path, but I have a string, a composable sequence of paths in my category. And I want to know whether or not some property holds of that composable string. Well, in this case, I can't expect to be able to contract everything down to a point and then test whether it holds. So instead, what I do is I contract it down to a single path and ask whether it holds. So intuitively, the kind of picture to have in mind here is that I'm not contracting my whole path. I'm contracting just these sort of outer bits of the path. I'm contracting it down a sort of sequence, composable sequence of paths to a single path, and then I ask whether it holds. And this is the intuition that the rule is going to capture. So let me state the rule. So I'll write the rule, and I guess someone will say at first that this doesn't work. And you're right, it doesn't, because I have to write something more at the end. Okay? So let me pull this down. No, I'm just showing what's going on in the context. Yeah. One way to think about it is that a groupoid is a kind of model of some sorts of states and transitions between those states, but in such a way that you know that if you can transition from A to B, you can always transition back in a way that more or less leaves everything alone. A category, on the other hand, is a model of a way of thinking about a bunch of states and transitions between them where you can't do that. And so if you want to know whether or not something holds of a sequence of transitions, you can't contract it down to a single state. You have to actually have some non-trivial transition in there. So here's the rule. So this is the elimination rule. So it says that if I've got x primed, x, y, y primed, all of type A, and I've got u of the Hom type going from x prime to x, and I've got a v of the Hom type going from x to y, and I've got a w of the Hom type going from y to y primed. Well, I'll write it here, and then I'll kind of refine it a little bit. So let me leave a little space there. So if I've got a type varying over all of that data, so over a composable string of 3 arrows, then, well, if I can contract those guys down, those outer guys down to reflexivities, and test there, then I should be able to test everywhere. That's the kind of idea. So again, I'll write this with a little space. So if I've got some E here, when I've shrunk all of those guys down, so x for x primed, r of x for u, y for y primed, r of y for w, then I'll put a star here because I'm going to say something else in a moment. Then I can actually do this in general. X primed, x, y, y primed, all of type A, u going from x prime to x, v going from x to y, w going from y to y primed, and maybe some other stuff. And then I get a j, e, x primed, x, y, y primed, u, v, w of type E. Okay, so this is the intuition. Intuitively, this is the rule you want to write. But you can't really write this. And the reason why is that, well, this rule is also valid in ordinary Martin-Liff type theory. And in fact, if you write this rule, this is interderivable with the usual elimination rule for Martin-Liff type theory. So I need some side conditions. And the point is that the world of types, when you start looking at directed things, is no longer as well behaved as the world of types was when you were looking at things being groupoids. So I now need some control over that. And the way I'm going to do that is that I'm going to state you have to satisfy some additional conditions in order to deploy this rule. So I'll write the second condition that I want first. So this is what I'll call the second side condition. And the second side condition says that, in fact, x and y must occur as free variables in E when I've made those substitutions. Now, so this isn't too bad, but this isn't going to get us very far because as I've stated it, you can't use the rule all that well. You need to add some parameters here, and that's why I've left this space, because I want to actually state the rule in a parameterized way. So I need some delta there, and delta with those substitutions here are x for u, y for y primed, and r y for w. And here I need delta again. And the second, or the first, as I like to think of it, side condition that you have to satisfy says that in this delta, I'm not doing anything nasty to the, I'm not making a bunch of additional assumptions about this sort of string of composable things. So it's a little like the conditions on free variables that you have for things like the universal instantiation rule for propositional calculus. You have to check this variable condition to make sure that you haven't gone and assumed something nasty before you introduced a universal quantifier. And so here I can't assume that I've got all kinds of wild loops on my y and things like that unless I know that it's actually going to appear here. And so that's the side condition one, is that if, let's say, z in the set x prime, x, y, y prime occurs in delta, then it also occurs in E. Okay. So I know this is a bit of a mouthful, but what I'd like to do now is to show you that you can actually use all of this to do something. Yes?
Are you assuming that E is in normal form or something? Because you can always make any variable occurring here.
No. So that's not true because, again, if maybe it's not here anymore, I'm only assuming I have a base type in these guys. So that's another point, is that if I add pi's and sigmas, these conditions, well, actually, this condition becomes more complicated. It has to be given by logical relations on the structure of E. So that if E was a sigma type, I'd need to know that the variable condition was satisfied both for the thing I'm summing over and the things that I'm summing. Okay? Similarly, for the pi, you would now have to put the thing you're taking the pi over into the delta and make sure that that variable condition is satisfied. And so all of this has to be given by logical relations when you start adding more types. But in this theory, you can't cheat and get those in there. Okay. Well, yeah, I mean, yeah, so does that answer your question? Okay. So there, you're right. There is something tricky if I allow more things that you have to be aware of. Okay, so yes?
I'm very confused that there's no covariance or contravariance.
So, well, that goes back to these design principles. That I want a theory where I don't have...
It would be nice to get rid of them, but I don't see how you can do without them.
Well, the covariance and contravariance is actually determined by the theory. So I now introduce the notion of covariance and contravariance on top of this theory. And then you can prove that if you've got a type that's covariant well, then you get a transport in the covariant direction and so forth. But all of that is built on top of this. It's not actually embedded in the syntax. So when you build models, for instance, you have to actually calculate all of that co- and contravariance information out of the syntax. No, I'm not going. No, I'm not. I'm sorry. As I said, I'm not going to talk about semantics today. So.
Are you going to define covariance?
No.
Okay.
But
I have no idea how to think about it.
well, I define it by induction on the structure of the types, right? And then, so, I mean, we know the base type is contravariant, say. You can kind of make a choice there. Or you can say it's just not variant at all. Then you know that the identity type is contravariant in the first position and covariant in the second position. So, and then you extend that definition to all types.
So can you add new axioms? Say, like, I suppose that there's some other type which is contravariant or covariant?
Well, if you have pies, then you need to say how they interact with this and so forth. So if you extend all of the types in the system, then you're going to have to also extend the definition of co- and contravariance, by again, presumably by logical relations. So, but I don't want to talk about that today. I want to just show you that this theory actually is very workable. And so what I'll do, well, I'm already running out of time, but if I have time, what I'm going to do is I'm going to prove that to every type there's an associated category. And then I'm going to prove that it actually is a category and not a groupoid. Okay? So, so let me, the computation rule I better tell you about. So let me make a few notes about this definition. So I've already made several of them in response to the questions, but let me make a few more. So I want to avoid so much notation. So I will write, there are several things. So we write, I will always write this as just x primed, x, y, y primed, u, v, w, and so forth. And I'm not going to write the types of everything. It's always going to be, these guys are in the same order. Okay, and the next thing is I write just j, e, u, v, w instead of writing out all of the x primed, x, y, y primed, and so forth. So those are all inferable from the types of these guys. So we don't need to write them. And the computation rule, of course, so comp.
So J is the name you gave to the rule, the elimination rule again.
Yeah. Maybe it's better to give it a different name because you can consider the theory where you have both the Martin-Liff identity type and this thing. But for now, I just call it J. So J, this is kind of the obvious point, is that J, E, R of X, V, R of Y is going to be just E. Okay. So that's the computation rule. All right. So there are a few derived rules that it's useful to have around. So we have derived rules. And the first one is a kind of, instead of having to always look at composable strings of 3 arrows, I'm going to say you can look at composable strings of 2 arrows instead. So it's a very simple modification where I assume, for instance, that I've got x primed, x, y, and I've got u and v, but I don't assume the w. And then I've got an e here, and similarly x, y, v, and let's just say delta primed is the thing where I've made the obvious substitution of type, or giving me e of type e primed. Again, e primed is where I've made the obvious substitution. Then I get, in the larger context, delta I get a J, which I'll write JL E UV of type E. And it's the kind of left version where I contract that first composite on the left down to a reflexivity. And you get a right guy. So in particular, I need with obvious side conditions. And SC2. And what is this? Well, it's J E U V R Y. Okay, so you can define it as that guy. And you get a right one too. So we also have, so this is the definition of this. So also have, well, if I've got x, y, y primed, v, w, delta giving me some e, and I've got x, y, v, delta primed giving me some e of type e primed, then I can get, in the larger context, the right guy. And again, this is with side conditions. So, well, what good are, let me give you one more, actually. So this one is the kind of, probably one of the most useful derived rules that we have, but the conditions are a little stronger. So it says that, so given a context, so I'm going to have a very ugly context, and what it's going to consist of is a big sequence of points, x1 up to xn of type A, and then it's going to just be a string of arrows, u1, going from x1 to x2, u2 going from x2 to x3, and so forth, up to u in minus 1, going from x in minus 1 to x in, and then some parameters delta. Okay, so I've got this big context with this big string of arrows, and I define, so let sigma I be the substitution restricting to just the UI, okay? So it just takes all of the guys appearing before the UI and it makes those xi, takes all of the guys appearing after that UI and makes them xi plus 1, and it makes all of the guys at the front reflexivities and the guys at the back reflexivities. So it contracts things down in this way. Then the rule is as follows. So then we have in-array elimination. And here I think I want in greater than 2, and I want 1 lesser or equal to I lesser or equal to n minus 1. It says that if I've got a context like this, let's just call it gamma. If I've got gamma giving me some e, and I know that gamma with sigma I substituted in gives me e of type E with sigma I substituted in, then I can get a general guy in that context, which I'll write as J in I E, and then all of the U1 up to U in minus 1 of type E. And here the side condition is stronger, so we have a strong SC1, and what it says is that all of x1 up to xn occur in E. And then we have the usual side condition 2, okay? So this rule, it may seem like it's not going to be too useful because you've got all this stronger side condition, but it turns out that this stronger side condition is pretty much always trivially satisfied in the cases that you care about.
Does it mean that you keep a trace in the formula of all the places where you've been?
It means that you can't do things like take something nasty in the context where I do, say, this, and then I throw in my delta some loop back, and I'm not actually talking about this guy, but this guy in my E. Okay? So it's to prohibit that kind of thing. But I'll say a little bit more about this later when I prove that we actually get categories, because that's where this is going to come in. Okay, so I can now show that we get categories, and with these rules at my disposal. But the first thing I want to do is I want to tell you what is the equivalence relation we're going to quotient by in order to get categories. And since I'm running out of time, I'm not going to. So if you aren't comfortable with co-inductive definitions and proofs by co-induction, then I apologize. But there are several very good references which I'll quickly mention on co-induction, because I'm going to give a co-inductive definition. So co-inductive. No? You can ask Peter and okay. All right. You sure everyone has? Okay. Well, all right. Then I'm not going to give you references. If you want references, come and see me afterwards. Yeah, ask me later. So what's the definition? Well, it's this. So this definition appears in probably more places than I'm going to list. The first place that I think I know it from is a paper of Eugenia Chung. There she gives this definition, and then she immediately afterwards says, but this definition is circular, so it doesn't make sense. Now we've got to give another definition, and then does. Actually, it's co-inductive. It is circular in some sense, but not in a bad sense. But where it really appeared in a kind of properly respected way was in the work of Lafont, Métayer, and Wojtkowicz's. YT. Oh, did I get it right? Yeah. And that's their paper on the Folk model structure on omega CAD, strict omega CAD. And the definition is this, that given a type, well, it's a modification of these, but it's basically the same. So let me tell you one thing before I do this. So note that given f going from A to B and G going from B to C, we have two ways to form the binary composite. Okay, so we have what I'll write as G composed on the left with F, which is J, where I now take V here, V, let's see, what do I want here? It's the left, so this needs to be F, G, R, C. And I've got a right composite, which is J, again, V, V, R, A, F, G. So you can rewrite these. This is really the left. So this is the J, L, V, F, G, and this is the J, R, V, F, G. So you get these two ways to compose, a left one and a right one. And this composite is going to be strictly unital in this F component. And this guy is going to be strictly unital in the right component. So we've got that. And now we say, maybe I better write this here so that people can actually see it. So this is the definition. So given A and B of type A, we say A is equivalent to B, and write A twiddle B when there exists a reversible f of type Hom type from A to B. Okay, so this is a definition by mutual co-induction. So I'm telling you what being equivalent is in terms of telling you what being reversible is, and now I'm going to tell you what it means to be reversible using the notion of equivalence. So here, f is reversible when there exists the following data, some f primed going from B to A, and some eta going from here f primed, and I'll write a big dot because I want to take this to be both the left and the right composite. So I'll write an eta dot into reflexivity on A, and epsilon dot going the other way, f primed R of B. And let's say for dot, either left composition or right composition, and such that those guys, epsilon dot and eta dot, are reversible. Oh, pardon me. Yeah, I guess what I want is this. Pardon me. Let me just put it this way. This is a little easier. Sorry. I'm getting a little ahead of myself. Yeah, so there exists an f primed such that, let's just say, f primed dot f is equivalent to reflexivity on A. F dot f primed is equivalent to reflexivity on B. And that's for dot, either of those composites, on the left or on the right. Okay, so this is the definition of equivalence, and it's when we quotient by this relation that we're going to get a category. So I need some lemmas about this notion of reversibility. So let me make some basic observations. So observation is that this is reflexive and symmetric. And if you've looked at the work of Lafont, Métayer, and Wojtkiewicz, you know that in order to prove that you actually have a transitive relation, you crucially use the strict infinity categorical structure in their proof. And so one of the crucial things to prove, to show that you have a category, is that in fact you don't require that strict infinity categorical structure in order to prove that this is in fact a congruence with respect to, so an equivalence relation that's also well behaved with respect to compositions. So let me give you, it is transitive, yes, but to prove that is non-trivial. So, let me give you a lemma. So I'm going to state several lemmas, but this one is kind of the starting point because they all basically look like this when you give the proofs. So it says that given, let's say, x primed, x, y, u, and v as usual together with a delta, and suppose that in this context I've got some phi, which is a term of a Hom type going from some, I don't know, A to B, say. Then if phi, when I've substituted x for x primed and r of x for u, is reversible, then so is phi. So this is a kind of elimination principle with respect to these equivalences, or the notion of being reversible. All right, so so how do we prove this? Well, since phi when I've made those substitutions, pardon me, I need one more thing. This needs to satisfy side conditions. So satisfying SC1 and 2. Okay, so the type needs to satisfy those side conditions.
Reversibility for things in a HOM type.
Yeah.
And now it's a thing in an E type.
No, it's in a HOM type. This is a HOM of E.
Of
Yeah.
E of some other
Yeah.
thing.
E is a type, and A and B are in E. Okay. So since this guy is reversible, we have the following data. Some x, y, v, delta primed, giving me some psi going back the other way. B, A, and where I do that substitution. So here it's x for x primed, r of x for u. And this satisfies the side conditions. So I know that that gives me then, by the elimination rule, x primed x u v delta, giving me j on the left, psi u v. And that's now of the appropriate type to be considered a kind of inverse of phi. So let's call this guy phi primed. And note that I've also got the kind of guys corresponding to these. Okay, so I've got those terms corresponding to those guys. So what we're going to do is just play the same trick with that data. So similarly, we have what I'll write as, let's just say, psi dot of type E, and I'll be a bit sloppy and avoid writing all of the context, but it's going to go from, let's see, I want my psi dot phi with those substitutions made into reflexivity on X, or on, pardon me, on A with the substitutions. And I've got a zeta dot going the other way, so where that's psi is this guy. It's the guy that we have by assumption. So this guy we know is reversible when I've made the substitutions. So I know that it has a kind of inverse. Being reversible means that you have an inverse up to equivalence. And so that I just take to be the psi. So yeah, it's the f primed there. But I don't want to call it phi primed because it's actually phi after I've made all of these substitutions. So then I need to bump it back to the case where I haven't made substitutions to get my phi primed, and that's what I do here. I use the elimination rule. And similarly, I've got this where I've made those substitutions, and here I've got, that should be RA, and this should be R of B with those substitutions. So by all of this, and that's for dot any of the different compositions, left or right. So by this, I get then J psi dot UV, now going from, that should be a 2 because I'm kind of bumping that up, pardon me. Let me make this type check, sorry. Psi dot is of type E. This is going to be ugly. Let me rewrite this, pardon me. I just want to do the substitution at the end. They're terms, so it will be E, A, A. Then it will be here the, what is it, phi primed dot phi, comma, reflexivity on A. And now when I've substituted in X for X primed, R of X for U. And here I want the kind of converse, where I'm at b, phi dot phi primed r of b, making that substitution. And yeah, I'm just using my elimination rule.
You don't have to actually.
Okay. Okay. Well,
But so these assumptions, these size, are the witnesses of these equivalences?
yeah, they're the witnesses of those equivalences. Yeah. Okay, so anyway, by elimination, I then get, let me just write it like this. I get something going from phi prime dot phi into r of a, and it's this j term. And similarly, on the left, I get the zeta dot uv going from phi dot phi primed into r of b. Okay, and I need to prove that these guys are actually themselves reversible. So how do I do that? Well, by co-induction, in order to know that these are reversible, I only need to know that when I make the substitution, they're reversible. But by the fact that I've chosen guys who are reversible as the data for these elimination terms, that already holds. Okay? So by co-induction, these are reversible. And that completes the proof. And there are many sort of additional lemmas that you want to be able to use that look like this, that tell you how to construct reversible or maps between terms using something like this kind of elimination principle. So I'm not going to write all of them down, but let me just give you one of them, which is the kind of most useful one. And the others you can sort out for yourself. So this is what I'll call the equivalence lemma. And it's going to be by the exact same proof, but now where I use the in-array elimination rule that I gave you earlier. So it says that given gamma as above, so gamma, remember, was that big context. I think it's still there. And the sigma I also. And gamma giving me some phi of type E bar AB, such that phi with sigma I substituted in is reversible, then phi is reversible. And here we want to satisfy, so satisfying strong side conditions. Okay, which means that I want all of the x's occurring in my string, as the objects in my string of arrows. I want all of those to occur in the type that I'm looking at. Okay.
Fundamentally, I don't understand what's the definition here. I know it's co-inductive, but is it a property, or do you reduce the type of reversible f's or something?
Right now, yeah, so this is all done externally at the moment. If you have co-inductive types around, then you can try to internalize it, but
No, that's not what I meant, sorry. But here you assume that these proofs of this reversibility, right? These
yeah,
size there.
yeah. Because I know that I've got essentially this, yeah.
So there is a witness of
So there is a witness, yeah.
in a sense it's a type of equivalences on the, without internalizing it even.
Maybe we can talk about this later. I'm not sure I completely understand your question, so. So, yeah. Well, I require that there exists an f prime, right? Yeah, yeah, I guess so. Yeah. Yeah, it's a structure. Yeah, it's an infinite structure that I'm specifying in this way.
It's not a property, it's an infinite structure.
Yes. Yes. Yeah. Yeah, it's an infinite structure of all of the inverses and then the sort of the units and co-units as they were, and then the witnesses that they're inverse, they have inverses and so forth. It's kind of all. Yeah, I mean, I'm not requiring that they're adjoint equivalences, for instance. That would be some additional property that they need to satisfy. Although I don't really know what the status of adjoint equivalence is for infinity, in the sort of strict infinity category cases.
There's something implicit in that model structure paper because they have to build it.
Yeah. Yeah. Yeah, I sort of vaguely remember that, but I'm not, yeah. Yeah, it's not, it's probably worth looking at again to see exactly what's going on there. Okay, so that's the equivalence lemma. Now let me quickly kind of sketch, because I don't have a lot of time left, how you use this to then construct a category. Okay, so I'm going to list a bunch of lemmas, and I'm not going to actually prove them because I would like to actually get a little further. So you'll have to take my word for it, but the lemmas that I'm going to give can all be proved using this equivalence lemma. So, or sort of mild variations on it. So for F, G, and H, well, let me write it out. So F is a term going from A to B in the HOM. G goes from B to C, and H goes from from C to D. We have the following. So 1, and there's something here that I haven't told you about yet, but I'll mention it in a moment. So you have the following equivalence. This is a delta of F, G, and H. And I'll say what that is in a moment. 2 H dot G diamond F is equivalent again to the delta F, G, H. And these two are where dot and diamond are, of course, going to be left or right composition. But here I require diamond and dot are not equal. Okay? So where one is a left composition and the other one is a right composition. And here, the delta is the ternary composition, which you get immediately by the elimination rule. Okay, so it's just J, V, F, G, H. Okay, so just to give you a kind of brief example, so e.g. 1 with, let's say, dot equal to right composition and diamond equal to left composition, we take F to be identity on A, let's say R of A. And then that gives you the proof there. So this is just going to be all of the usual kinds of ways of doing this stuff, but it all has to be kind of done in a slightly more subtle way than for ordinary identity types in order to actually get a category.
The ternary composition is quite useful. You can derive the two left and right by just putting identity.
Yes, that's right. Yeah, that's yeah. I mean, the ternary composition is the real composition in some sense, and the other ones are just derivative of it. Yeah. So let's see. What else do we have? So let's say 3. We've got a kind of unit law. G F equivalent to G diamond F, and sort of another one like that, which is G dot F diamond R of A equivalent to G dot F. And this one holds for any of them, so it doesn't matter if they're the same. They're allowed to be the same here, the dot and the diamond. And the next thing that you need is whiskering. But I'm not going to go into that too much. So we have whiskering. So if I've got a big higher dimensional cell somewhere in here, phi, with this boundary, and I've got some h, or similarly, if I've got over here some psi, then I have a sort of left whiskering and a right whiskering. So I've got, let's say, h whiskered with phi and psi whiskered with h. And this one will have, so in this position, it's strictly unital. And in this position, this one is strictly unital. So if I plug in a reflexivity here, it's actually equal to phi. If I plug in a reflexivity here, it's equal to psi. So these are whiskering. And I don't want to go into whiskering in detail, but we have whiskering. And what you can prove is that, so there are kind of several facts. If at a fixed dimension, well, let's say at a, if at higher dimensions, equivalence is transitive, then one, this guy is a congruence with respect to whiskering. And two, this guy is, so these guys, left and right composition, are unital up to this guy. Okay. So you need to know that if I'm allowed to, at some stage, to assume that this guy actually is transitive, then I know necessarily that these guys are congruences and that I actually have the unit laws at that stage. And you use this together with one other fact, which is the kind of distributive laws for whiskering, to prove that the twiddle is transitive. So the lemma is that this is an equivalence relation, and the proof is, well, you have to verify it using co-induction, but so it's by these facts, and so those facts and the other facts I gave there, and the distributive laws up to twiddle for whiskering, which you can easily see to hold. Okay, so that gives you that. And the immediate consequence is then the theorem that each type, so a type A has an associated category. Pi 1 of A with, well, the objects in this category are just the terms in that type. And this can be done, of course, in context, too. So there's just the terms in that type. And with the HOM, pi 1 of A, AB, the obvious thing, it's just those terms F of type HOM AB modulo equivalence. All right, so in fact, this isn't just a group, so it's a category, but you might worry that it actually could be a groupoid, that maybe we haven't somehow ruled out the construction of inverses. So let me very briefly sketch the, I'm not going to go into detail because we're running out of time, but let me just sketch the idea of how you prove. I mean, there are various ways you can prove that you actually get a category. One is to construct a model, but I've told you I'm not doing semantics today, so I'll give you instead a kind of proof theoretic way to see that you actually have something that's really properly directed. So I'll construct some machinery. So given a context, gamma, let G sub gamma be the graph with vertices, let's say, those variables, let's say little x of type B, where B is our base type, declared in gamma. And an edge in this thing will be, again, it's kind of the obvious thing, it will be a variable, let's say v of type hom in B from x to y, where those guys are variables, okay? So I don't care about other things, I just care about the variables. So variables in gamma, yeah. Then I extend this to arbitrary judgments. Extend to G sub gamma gives me J. So I've got a judgment in context gamma, and I construct this guy as follows. So by analyzing, of course, the structure of J. Okay, so if the first case is that G gamma proves A, I just define to be the same as G gamma. Okay, so if you're deriving a type judgment, I just don't care at all. If you're deriving a term judgment, A of type A, then this is going to be, well, it's going to be, I need to look at what this A is. So if this A is itself a hom type for the base type, then I will add something. So it will be G gamma union with an edge, let's say F, or let's say V, I guess, from X to Y, when A is equal to the base type hom XY. And the X and Y need to be vertices. Okay, so they need to be variables declared in gamma. Otherwise, it's just G gamma. And similarly for equality, so if it's an equation between types, I just take G gamma. If it's an equation between terms, I just take G of one of the terms. Okay, so I've got these guys.
So that could be equally said by just adding A to gamma and taking what you want to know.
Yeah. So now I'm going to formulate a property of the type theory, which is going to ensure that we actually have something really directed. So so we're going to construct a functor. So I start with a graph, and then I take the free category on that graph to get a category. Then I take the preorder reflection to get a preorder. I include that in cat, and then I forget to get a graph back. And I'll call this guy flat, because it kind of flattens out your, sort of takes your graph, composes anything that can be composed, and then it flattens it out. So then we have the definition, which is that a judgment gamma proves J is well directed if and only if g at gamma, when I flatten it, is equal to g at gamma proves j when I flatten it. And the theorem then is that every judgment is well directed. And the proof is just by induction on derivations. Of course, there's a lot hidden in saying it's by induction on derivations. You have to do a lot of case analyses to see that the induction hypothesis will actually allow you to construct the composites that exist when you've substituted after you expanding it. So, but yeah, it's these. So if the judgment is that I've got it, maybe it's hard to see from there. Yeah. So, well, what's the consequence of this? The consequence is that the theory is actually does not allow you to derive symmetry terms. So you cannot derive inverses of arbitrary edges. So that's a kind of corollary. Is that the theory is really directed. In particular, if you're in the context, so here I literally mean this, I'm not assuming anything else out there, but I've got x and y of the base type and v in the base type HOM going from x to y, then it does not follow that there exists in that context a term tau of type byx. Okay. So I think I'll stop there for today, but that's the result. So